Welcome to our talk on human-based versus automatic feature ideation for time series data. This paper is the result of collaborative work between Johanna Schmidt from the VIA-WIS Research Institute, Harald and Thomas from the WIS-Plor GmbH, and Jürgen from the University of Zurich and the Digital Society Initiative Zurich. Feature extraction is an important part of many data-driven approaches, like clustering or categorization. Feature extraction defines the process of transforming raw data into compact, numerical data representations while preserving relevant information of the original dataset. Feature extraction can be divided into 4 steps. Feature ideation is the extraction of raw features from data. Feature transformation describes changes made to these features. Feature generation is used to provide more precise representations of the features. And finally, feature selection leads to a reduced set of possible features. In this paper, we specifically concentrate on feature ideation. Feature ideation is the first step in the pipeline, where features are extracted from raw data. Feature ideation is also often called feature extraction or feature discovery in the literature. This step is in many cases immediately answered by applying automated methods. For example, these are the typical feature engineering techniques mentioned in Wikipedia. Unfortunately, for domain experts working with data, who are neither experts in statistics nor in mathematics, these automatic approaches are very hard to grasp. In our research, we focus on the ideation of features from time series data. For example, look at this time series dataset. It represents inflation rates from different countries over the years 1960 to 2021. Several patterns stand out, for example, such as peaks in the crisis in 2008, or the difference between Pakistan and the European countries in the 70s and 80s. A non-exclusive set of typical automatic ways to extract features from time series are piecewise aggregate approximation, perceptual important points, discrete wavelet transform, or similar, or statistical methods like computing the mean gradient. For more information, we refer the interested listener to surveys cited in our paper. However, we notice that in many cases, domain experts want to define features with domain knowledge in their head. In many cases, phenomena in the data can be better characterized through the knowledge of experts, requiring features that cannot be captured with general automatic methods easily. When looking at the inflation rates again, domain experts may, for example, need discriminative power in distinguishing countries with low inflation rates, so between 2 and 3 for a longer time period, from other countries with high values over a longer time period. Or they might want to classify countries according to how much the inflation rate increased during a financial crisis. For example, the economic crisis starting in 2007. Given this duality in feature ideation approaches, we believe that visual analytics is highly appropriate to be applied for feature ideation, as it fosters to keep the human in the loop. Visual analytics helps domain experts to stay in control of the feature ideation process if needed, allowing them to include their own knowledge into the process. Interestingly, feature ideation is a comparatively blind spot in visual analytics research. As seen here in this table created by Parmpas et al., visual analytics research approaches have mainly concentrated on feature selection so far, but not on feature ideation. Accordingly, the table cells for other stages of the pipeline are still relatively empty. So we think that it was worthwhile to look into how visual analytics techniques can support feature ideation. We conducted a study to compare 6 automatic methods for feature ideation in time series with 2 human-based methods. We used one dataset for our study, which stems from Industry 4.0 sensor recordings. The data reflects the production process of fire bricks, where presses are used. The time series show the force of the presses during production. We had 526 time series in our dataset. This is how the time series look like. Force is built up inside the press, then the pressing is done at maximum force, and then the force dismantles. The colors show that the pressing processes have been recorded in 4 different factories. The domain experts wanted to find out whether they can find distinguishing features to classify the pressing procedures according to in which factory they have been produced. These are the automatic methods that we used. Some of them, like the piecewise aggregate approximation and discrete Fourier transform, have already been mentioned before. More details can also be found in our paper. We decided to also include the raw data as a feature. For calculating the automatic features, we used existing Python libraries. For the human-based methods, we used Visplore as a visual analytics tool, and domain experts extracted 2 distinct sets of features by interactively defining features. Users can, for example, set the time the presses spend at maximum force as a feature. It is also possible to categorize time series based on their gradient at a very specific point in time. Or users might want to use a time series spent in a certain value range as a feature. The human-based features have been exported from Visplore into files to be later used for the analysis in the study. To evaluate the generated feature sets, as generated by automatic and by human-based methods, we defined 7 feature characteristics. Parameter sensitivity defines how many parameters are needed to ideate a feature. We calculate parameter sensitivity as a combination of the number and sensitivity of the needed parameters. Computational scalability defines the time needed to compute the feature set. Redundancy is defined by the strength of the correlation between the features in the set. Size defines the size of the feature vector. Retrieval performance defines how well the feature set can be used for querying the data. We computed the error of k nearest neighbors with all time series. Classification performance defines the suitability of the feature set for a classification task. We applied a trained random forest classifier and measured its performance. And finally, self-explainability is defined by how well users can semantically interpret the feature set. Here are the results from our analysis. In this table, you see the ideated feature sets as columns, the 6 automatic methods first, the 2 human-based methods on the right. In the rows, you see how well the feature sets performed according to our 7 defined feature characteristics. Green plus means very good, orange omega means mediocre, and red minus means bad performance. The overall results show that human-based methods provide comparable performance with automatic methods for most criteria. The results for the automatic methods show a high heterogeneity. Obviously, choosing a suitable feature ideation method for a given dataset is a challenging task. Parameter sensitivity, so the selection of parameters, and computational scalability generally show really good performance for automatic methods. The same applies for retrieval and classification performance. Automatic methods are well suited for both tasks. Definitely the biggest drawback of automatic methods is their lack of self-explainability. Human-based methods in general show a low degree of redundancy and feature size. The retrieval and classification performance of human-based methods is comparable to the automatic methods. The biggest advantage of the human-based methods is definitely their high degree of self-explainability. The biggest drawback of the human-based methods is the manual interaction, which opens up a huge parameter space. Our results show that human-based methods can compete with automatic methods for feature ideation in time series data, and that visual analytics serves as a proper technique for supporting human-based feature ideation. So this is definitely a call for action in terms of studying the usage of visual analytics in the feature ideation process. We are aware that our study has some limitations. We conducted the study using only one dataset. Our domain experts had a relatively clear idea about how to define features, so no exploratory setting was needed. We are also aware that human-based feature ideation is not needed in all cases. With our study, we also wanted to pinpoint directions for future work. Since feature ideation is a comparatively blind spot in visual analytics research, we think that novel visual analytics techniques for feature ideation in various domains could be an interesting research topic in the future. Since human-based feature ideation is not needed in all cases, and automatic methods may perform well for classification and retrieval, decision systems for users who have to decide between a human-based and an automatic approach are of interest. We did not touch the topic of exploratory settings in our study, but in cases domain experts do not have such a clear idea about feature ideation, exploring the possible space with visual analytics techniques might be helpful. We also thought of initiating a conceptual workflow in the future, which might consist of exploratory data analysis, leading to be able to do informed feature ideation with the possibility to retrieve a new automatable feature ideation process from it. More ideas about future work and the way how visual analytics applications have to be structured to support feature ideation can be found in the paper. We hope we could awaken your interest for human-based feature ideation with the help of visual analytics. With that, we would like to thank you very much for your attention.